Okay, hopefully this is all set up and working. As usual, could you stick your name in the chat if you are there, so it helps with the register and to know this is all working correctly. Hi Tom, hi Aidan, hi Adam, Jack, Toby, Joe. In fact, as usual, we'll stick the I'll stick the chat over here in a minute. Okay, did you all have a go at the finite state machine lesson last week? I mean, it was the one we did as the taster session, so you have done this before. Hopefully it all came flooding back. Whoops. And that was the activity at the end. Anyone have any particular issues with this? Anyone got any questions about this one? See if I can arrange this screen a bit better. Let's put this up here. Put this here. And then we can put the chat in here so you can all see everything. Okay, I think that'll work a bit nicer. Let's do. Okay, so Adam, converting them. Yeah, we're going to look a bit at converting today. There is no just method to follow to do it. It has to be pretty holistic the way you approach it. So you take the finite state automaton, you figure out what it's trying to do, and then figure out a regular expression that will do the same thing. There's no sort of secret technique to it beyond that. But we'll go through the answers to these, make sure this is what you were expecting them to be. So the first one, a finite state automaton with an alphabet of A and B, which accepts any string with an even number of A. So as I said at the time, this depends whether or not you want to accept 0 as an even number, as to how easy it is. I'm going to say 0 isn't an even number. I'm going to do the full one. So, I'll click on the wrong thing. Here we are. So if I put in my first state, which would be the start state, and then once they click once, it will be an odd number. So once they enter an A once, it will be an odd number. When they press it again, it'll be an even number, and we only want to accept when it's on an even number. So pressing A will take them to there. Pressing B will also take them to the odd one. So anything they press, actually nope, that won't, my mistake. Now pressing A will take them to there. Pressing A again will take them to even, and pressing A again will take them to there. So now we press A, press it once, twice, 3 times, 4 times, 5 times, 6 times, it's an even number of A's we'll get to there. But the alphabet, as was said, is A and B, so we have to tell it what to do with the B's. So B does absolutely nothing in this because it's only the number of A's we're counting. So B will always stay in the same place. It doesn't affect anything. So that will be the finite state automaton for an even number of A's. Okay? Again, if I make a mistake in this or get anything wrong, flag it up in the comments. I'll correct it. Right, the next one was an FSA with an alphabet of A and B which accepts any string which ends in AA. Okay, so for this one, well, we'll start by saying that one. So an A is entered, it's that. Another A is entered, will be there, and this is where we start. So once we've started, if we enter A once, we're in this state where we've entered 1A. If we enter A again, we're in this state where we've entered A twice, and that's going to be the accept state. That's the start state. But we also need to say what happens if they enter a B or if they enter another A after this is done. Well, it has to end in A twice. So if they've entered AA and enter another A, that still is entering A twice because it's AAA, and that still ends in 2 A's. So another A here will just stay there because it's still going to be accepted. But if at any point a B is entered, we go right back to the start because they have to be able to enter two A's after each other, and a B would break that up. So if at any point they enter B, back to start, and they have to enter 2 A's again. So that's the second one. The third one accepts exactly the string ABBA, well, it's going to start here, and we'll put in all the different stages of doing this. So once they enter A, they go to there, they enter B, go to there, enter another B, they go to there, enter final A, go to there, and that'll be the accept state. And the only way to get there is from start. Typing A will get you there, and from A, typing B will get you to that one. From B, typing another B will get you to that one. And from B, from there, typing A will get you to that one. But again, we have to think what happens if they type something else. And this one has a sync state. This one is if at any point they type something other than ABBA in sequence, there's no way now to ever get to the accept state because it can never now be ABBA because there's something else in there. So every incorrect entry leads down here. So typing a B at the start means we're down here. Typing an A after the first A leads us there. Typing an A here, or typing a B here, or once ABBA has been typed, typing anything will take us there. And also, once you're in the fail state, there's no way out. So I think it does work putting A, comma B in there, but I'm not certain, so I'll just do it the long way. So that's going to be the FSA for typing exactly ABBA. So that is any verification routine, password checking routine as a finite state automaton. And then finally, the complex one, which I remember in the taster session a few of you got, which is very impressive because most years we don't get people getting that one, is it has to contain A, B and C, but in any order and anything else. So again, we'll work through it logically. We'll do in the start on here. Then, after the first thing they type, they can either have typed A and be in a state where A has been typed, they can have typed B and be in a state where B has been typed, or they can type C and be in a state where C has been typed. So from the start state, you press A to get to there, B to get to there, and C to get to there, and that's the start. So on the second type, if they're in the A state, they've already typed A and they press A again, they're still in the A state, because ultimately that's what's being typed. We don't care how many of each letter, we're just looking for whether or not each letter has been typed. If they're in A and they type B, they will go to the AB state, because both A and B have been typed. If they're in B and they type A, that will also take them to the AB state, because still here A and B have both been typed. There are two ways to get to A and B both being typed. If they're in B and they type B, nothing changes. And then from C, if they type A, we'll go to the A, we'll go to the AC state. And if they're, if they're in A and they type C, they'll go to the AC state. And if they're in C and they type A, we'll go to the AC state. I'll make this a bit more readable. And then the other state they can be in, if they're in C and they type B, they'll be in the BC state. So being in B and typing C will send them to there. Being in C and typing B will send them to there. And in each of these, and this one I am going to do it with the commas, if they're in there and they type A or B, they will remain in that state. If they're in this one and they type A or C, they'll remain in this one. And are in this one and they type B or C, they'll remain in that one. And then finally, they can all from this one get to an ABC state, which is the accepted state. And from AB, they need to type C to get there. From AC, they need to type B to get there. And from BC, they need to type A to get there. And finally, once they're there, it doesn't matter what they type, they have already typed ABC, nothing will change that. So A, B, or C will leave them in that state. So that will be the finite state automaton for checking if all of the letters A, B, and C have been used. Okay. Does anybody have any questions about that? Anyone confident they did get all 4 of them done, and having looked at mine, they're happy that all 4 of theirs were correct? There's a loop missing on C missing. Yep, you're right. If you're in C and you type another C, it doesn't move you out of the C state. Well spotted. Okay. Right, so just before we move on to the next bit, which is how we then do all of those as regular expressions, I'm just going to quickly do a register to see who did show up, so to make sure the YouTube ones are working. So Will, you've not written anything there. If you're there, write something now, because it looks like you're currently not. Ed is there. Ryan, yeah, Ryan is there. Tom, Yep, Tom's there. Stephen. Yep. Tobias. Toby, yes. Cameron. Yep, Cameron's there. Jack. I've already seen. Yep. Joe. Yep. Ben. Yep. Adam. Yep. Jonathan Owen. No Jonathan Owen yet. Margot. Yep. Aidan. Yep. Beth. Yep. Jonathan Wadding. We're missing both Jonathans, I think. And Dylan. Still no Dylan. Okay. So we do have Ryan, but we don't have Jonathan, otherwise it's the same as last lesson. All right. So in the exams, once you've done finite state automatons, once you've done regular expressions, the most difficult question they'll ask you about those is to say, represent this finite state automaton as a regular expression or vice versa. Now, is that broken or is that just a picture Jack has posted to try and make things look difficult? I'm not sure if I think the chat might be playing up again. Okay, the Teams chat is there as well. So if there's a problem with the YouTube chat like last week, you can comment in the Teams chat and that will show up. Put that like that. Okay, it is a picture. Very nice. Okay. Yeah, so let's have a look at these ones to begin with. If we go back to the start one here, let's say from this perspective it's quite easy because you're given the context of each one. So we're told an alphabet of AB which accepts any string with an even number of A. So what you're doing essentially is trying to come up with a regular expression that accepts any string with an even number of A. If you're just given the finite state automaton, so you're given that, for example, and told make a regular expression that does the same thing as this. The reason that's so difficult is first thing you've got to do is figure out what this is doing. Once you've worked this out what this is doing, as in it's allowing anything with A, B or C in there, then you work out how to do it the other way. So we'll have a look at some that have appeared in exams in a minute, but let's do these ones first. Well, let's start with this one since it's right there. Let's get this up. It's working now, so it's behaving weirdly the other day. No, it's behaving now, good. Okay, so coming up with a finite state, a regular expression that accepts a string as long as it has an A or B or C in there somewhere. Well, I would probably go for something like this. Well, it can be one or more A's followed by one or more B's followed by one or more C's, or one or more B's followed by one or more C's. Oh, that's not an end. Followed by one or more A's, or one more C's, followed by one or more A's, followed by one or more B's, and keep going like that for all the possible permutations of it. That's the one that immediately springs to mind for me. Did anyone do that in a different way? Anyone find a more efficient way of doing that, or one that involves less effort, or just a different way altogether, not necessarily more efficient? Anyone come up with a better way of doing it? Right, oh, right. You're on a good. See where we're going with this one. It needs a bit more, Ed, but let's start with that. See if we can make that work. So you've gone for A, or B, or C plus. The reason that's not going to work at the moment because that's any one of those, one or more. So if I just put A, that would match that. So I've done the A one time. I'm trying to think if there's anywhere I can go from there that would then make me do it another time, but there isn't. So I put that again. No, it's not going to, I can't think of a way to take it from there. The problem with that one is that's going to allow a single character. Hang on, you put A or B or C. So I don't know what the extra brackets are in there. Probably does the same thing as that one there. No, anyone else have a different way of approaching that? No. Okay, so assume this method is as simple a method as we can get. It's quite a big complex one, but it was also quite a big complex finite state automaton. So that in the end is just a difficult one to do. It's a complex one. Let's have a look at one of the easy ones. So the one that accepts exactly the string ABBA and nothing else, that's definitely the easiest one to do as a regular expression. It is just that. There's no symbols need using it. It has to be exactly that. It's not one or many. It's just that. The one where it says an even number of A's. Oh, Tommy's just posted one for, is that the ABC one? Let's have a quick look at that, see if that might work another way. So A plus BC or CB plus. I think we might be onto something here. This doesn't quite work because this one requires us to start with the A. So something like BAC wouldn't get accepted. Now, is there a way? No, because this doesn't work with things like ifs. We can't say do this, and if this A hasn't been done, then there has to be one here. There's no ifs and thens. That's not going to allow us to start with anything other than A. It is more efficient if we do start with A, but because we can start with B or C, that one's going to have issues. So yeah, I really think this one up here is the best way we can do it, and it's a long string, but it would work. I mean, as we saw last time with in the mark scheme with the Claire, pipe Claire, what would be a valid answer for this, although it feels a bit wrong, is just to go oh no, that wouldn't work, sorry. It's that one there, ignore me. Okay. So, anyone figured out how to do the even number of A's? Could you post a suggestion? Of course, yeah. Yeah, good point. Yeah, sorry. There has to be a plus after there as well. Sorry, I thought that I'd just missed that out. Yeah, the plus is after there. It says there has to be one or more of A, B, or C in that order, and then any number of them after that. Right, so anybody figured out how to do the one for an even number of A's? A regular expression that would accept an even number of A's and any number of B's. Nobody? Or his comment's broken? AA or B 0 or 1 times. Well, that's not going to work because anything with a star in it means you can enter nothing. So if you do nothing at all, that would be accepted. So, which obviously isn't what we want. Also, we said or B, well, that would allow B any number of times to be accepted. So let's just blank this. I don't want to save it, I want to do anymore. So for this one, we know we need to have AA. However, and that has to be 1 or more times. So if AA, or we have AA, that's fine. That's going to work. But we can have B's in there wherever. So we can have any number of B's beforehand or any number of B's afterwards. Look, A, B, A also has an even number of A's. Yeah, it does. Yeah, I haven't got that one yet. Okay, so by having the two A's together, that would work there. Actually, yeah, that would do for that one. There's also, as Margot points out, ABA has to be accepted. So we could have something like n number of B's A, and that any number of times would cover there being an A at the start and end with a B in between. So if we put those two together with a pipe, I think that covers the A's being together and surrounded by B's. It also covers any number of A's with a B in between. In fact, we can make that more efficient if we say A, B, star, A. In fact, does that do it? I'll put the whole thing. Yeah, I think that does it. That's the most efficient one I can come up with. Would that work? I think it would. Like I say, this is why this is difficult. There is no fixed way of doing this one. It's all holistic. It's all solve the problem approach to it rather than just following any set algorithm, which can be fun, but in a timed exam and under pressure, these ones can often result in a bit of a meltdown. Okay, can anyone see any reason that wouldn't work? Because I think that would do it for the even number of A's with B's anywhere at all. Okay, the next one is an easy one, and I do want people to post some suggestions for this one. Any string that ends in 2 A's. This is a very easy one. Can you post your solutions to that one? Because you should all be able to do this. So any string which ends with AA, what's a regular expression for that one? Yeah. Yep, that's that one. So anything at all to begin with. So A or B, any number of times, as long as at the end it's AA. That would be fine. Yeah, so that's all of them. So actually, it seems like you guys are better at creating finite state automatons than regular expressions. So I'm going to have a look, see see if I can find some of the example. Whoops, that's not what I meant. Drag the wrong bit. This is the bit I meant to drag. Okay, so if we do, what's it called? Example. In 2 seconds, I'll get some past exam questions up, and we'll have a look for some where it's specifically giving you a finite state automaton and ask you to convert it to a regular expression and see if we could do them. Okay. Okay, so here's a question. Ignore part C, we're just going from this one here. Won't let me scroll any lower. I'll move it up like that, might help. There we go. So it says the diagram shows a finite state automaton that recognizes a language. Recognize those ones. Write a regular expression that would recognize the same language as a finite state automaton in the diagram. So like I said, there isn't a algorithmic way of solving this. There isn't a do this step, then this step, then this step, and now you've converted it. That's what makes these so difficult. So what you've got to do is look at it holistically, look at it from the point of view saying, well, this goes to this, so this might work, or figure out what the rule is for this. And once you figure out the rule, then work out a regular expression that will do it. So it's a 1-mark question, this, and I think it's one of the most difficult 1-mark questions that appear in the exam. So it's one of those that if you can get it straight away, do it. Otherwise, you leave it till the end and come back and do it when you've got time left over. But I'd like everyone to have a go at that. See if you can come up with a regular expression that would do the same thing as this finite state automaton. Okay, I'll leave you a couple of minutes to do this and then pop back. Okay, right, some really good, I'll move this up so the later ones are still visible. Some really good discussion. I'd see a few more people engaging with it, but some really good discussion going on. Yeah, we started out with people saying, well, it has to be A, C, star somewhere in there. And then we realised, hang on, B's don't necessarily end it. It has to be the ability to do it again after the B's, and a few ideas come in. I think, ignore that. I think Tom's seems like a pretty good one. So Tom's one here of A, then in brackets, B, A, pipe, C, star, seems pretty efficient. Anyone seen a reason that wouldn't work? So I'm looking at that and that seems pretty good to me. Let me just go check the phone, it'll be 2 seconds. Okay, back. It was a scam call. Right. Yeah. Look, I think Tom's the first one. I think Tom certainly seems to work as far as I can tell. That's obviously a reason that's not going to work. Margot's gone for the same as Tom's on that one. That's Adam. Beth's of A, followed by any number of BAs, followed by C. That certainly seems to work as well. Because you go A, then BA will turn you back to there, then a number of C's. I know, Beth, the reason yours could be a problem is if you A, B, C, and then do another BA, that would still be accepted. That isn't covered by yours. Because yours, the C can only come at the end. And on this one, it doesn't have to be C at the end. C can be in the middle. So I think the one that Adam, Tom, Margot, well, that seems to be the nicest way to do it. It's not the only way. There's always multiple ways of doing it. But let's see what it says in the mark scheme for this. So this was part D. So yeah, these are a few that would be accepted. So some example correct regular expressions are listed below, but award a mark for any regular expression that would correctly represent the language accepted by the FSA. So you're kind of hoping the examiner is good enough to figure this one out. So there we are, A, BA, C star was in there. That bracket around there isn't necessary because we know about the order of operations with pipe. But yeah, that's the one that we went for in the end. These are accepted, but there's a few different ones that would be done. I'll see if there's another question like that with a conversion in it. Nope, that's a simple one we did. Nope, that's about it. So in terms of past papers, because it's only been on the spec for a while, that's the only one that's come up so far. It's given one of those and asked us to do a conversion. And we got there eventually, but it seems an awful lot of work for a 1 mark question. Okay, so we'll move on to the next topic in a minute. So has anyone got any questions at all about finite state machines, regular expressions, converting between the two, anything like that? Anything you want to bring up now? If not, we'll move on. Right. Okay, so I'm jumping around this topic a little bit because I'm sort of loading up the ones that are easier to do online, because I know hopefully for most of us we'll be able to have some face-to-face stuff soon. I might do a bit of stuff in there where it's a bit easier. On that, by the way, in case you've got any questions about next week, I still haven't been sent the list of who will be in the class and who's doing what. I understand you guys have, but it's not exactly unusual for this school to tell you guys stuff before they tell the staff. So I don't know who is there and who isn't. I don't know who's not coming in at all, or who couldn't be timetabled so that all their lessons fit on one day or whatever. When I get that, I'll work out what I'm going to do. So I think what's easiest, if you know you are going to be in the Monday lesson, let me know here, so at least I've got a preliminary one. I assume some point today they are going to send me that list, because obviously they have it, but they've not sent it on to staff at all. Yeah. So I think if you are doing a more typical set of A levels, like maths, physics, computer science, chemistry, or those grouped together, then will fit nicely in and you'll be in on Monday. If you're one of those nutcases that does the strange combination like philosophy, modern dance, and computer science, then they couldn't really find a way to make it fit. So there'll be a couple of people that aren't there. And the government has set very strange rules for this. They've said there can only be 25% of the school in at any one time, and you cannot come in and then leave again. If you come in, you have to be in all day. We're not allowed to do a rota. We're not allowed to say you come in just for the morning and then go. That's what's caused the problem. No idea why, but that's on the official guidance that we're opening, is we cannot do a rota. If you come in, you have to be in all day. So that's a problem. So the only way we can make this work as best as possible is to say, well, if you're in for a whole day, we do it for the most typical combinations of A levels, and you have all your A levels at once. Because we can't say come in twice a day, because then if everybody comes in twice a day, we're going to have more than a quarter of the school in on any one day, so we're not allowed to do that. We can't say come in Monday morning, do computer science, and then go home and the next lot come in, because we're not allowed to do a rota. So yeah, the government has strung together very arbitrary guidelines, and we're working like crazy to try and make this work. So if you are in on Monday and you're in computer science, great, I'll see you then. If not, I'm still going to work out what best to do, depending on numbers I get. If it's just a couple of people that are there, what I'll probably do is just set up a camera at the back of the room and stream the whole lesson live. What I would like you to do ideally is to actually have a microphone, and I'll have earphones in or something like that, so you can actually speak and you'll be part of the class there. We'll try and do it as a virtual one for people that aren't there. If it turns out I only got half the class or something like that, what I'll probably do is, rather than cover anything new, I'll take that as a chance to do some question and answer stuff, to do some revisiting, so you won't miss out anything if you're not there. But it depends on what kind of numbers I get. So yeah, it'll either be the whole lesson will be live streamed and I'll have earphones in so I can hear if you want to say anything, which we'll test out on Monday, and I don't see any reason why that shouldn't work. Or something different, but until I get the full list, I don't know. Right, so we'll go back to the that's not what I want. Not that one. This one. Okay, so we're skipping at the moment because this is one I'm going to leave to a bit later. We're going to jump ahead to this one, which is a model of computation, a Turing machine. Okay. I'm going to assume at this point no one's heard of a Turing machine before or know anything about one. Does anyone know anything about Turing machines? Okay. Heard of it. So Tom's just gone for yep. Okay, so Tom, what do we know about Turing machines? Sort of, Aidan. It's not the basis of modern computers as much as it's an abstraction of computers. It's what a computer can do, simplified down as simple as it can go. So, has anyone seen The Imitation Game, the Alan Turing movie with Benedict Cumberbatch in? If you've seen that, then you might think a Turing machine is an AI simulation of his dead boyfriend. That movie was appalling in terms of historical accuracy. There's a guy from GHCQ who was quoted as saying, the movie did get two things right. Turing's first name was Alan, and there was a Second World War. Other than that, it's complete and utter fiction. So, the film's fun, but it's a complete fiction. There is almost nothing in there that is even vaguely accurate to what Turing was like as a person, what Turing did, what GCHQ was like, what Bletchley Park was like. It's about as accurate as The Greatest Showman is as far as P.T. Barnum's history. So don't take anything in there as thinking it's real. So yeah. So what a Turing machine is. This is, I'll give the whole history of it. I think I wrote a lot of it down in here, so I'll put this up first. Okay. Right, so a Turing machine, let's level up correctly, go back into there. There we go. So it's an abstract theoretical concept. Now, you've got to bear in mind, I've given the history of it. I don't think I have. No. So this was back in the 30s that Alan Turing came up with this idea. He came up with a concept that a machine could be built, theoretically, that does this. And that, therefore, that machine could be made to do anything, to solve any problem that can be solved. Now, bear in mind, this is in the 30s. This is before Colossus, which was the first programmable computer. He came up with a concept and a mathematical proof that a programmable computer could be made, that it is possible, and also that there are some things that that programmable computer could never solve, that there are some problems that are unsolvable, before the computer actually got made. It was an incredible mathematical feat. But what he came up with was this. The idea that a Turing machine consists of a finite set of states. Remember, a state, like a finite state machine, is just, this is the state we're currently in. It can be called anything, it can represent anything, it doesn't matter. But there's a fixed number of states that computer can be in. It also has a finite alphabet. So these are the possible inputs it can take. It has an infinite tape. Now this is the point where it becomes a conceptual model rather than a real thing, because obviously in reality we can't have an infinite tape. And that tape is marked off with squares. Then a sensing head can travel along the tape one square at a time, and rules for transitioning between the states exist to tell it what to do. So if we look at this, this is the machine here, it's hovering over this and it's reading a 1 there, and it knows it's in a particular state. Now these rules are what make a particular Turing machine do a particular thing. So each time it reads 1, each cycle, each clock cycle essentially, before clock speeds were a thing, it reads the value of the current square, it reads the current state, and then it writes a value and moves one place left or right. So the rules have to tell it what to do in what circumstance. So in each cycle, a Turing machine takes the current state and the character, and based on the current state and the character, changes state, changes the character, and then moves in one direction. So 2 inputs and 3 outputs. Once we look at an example, this becomes a little clearer. So the rules are usually given as a set of transition functions. So here's a transition function here. This sigma thing there is just, I don't know, it's used, I don't know why. But what it says is, if you're in state 2 and you've read a 0 on the tape, then you go to state 0, you write a 1 on the tape, and then you move that way. So if in the case of that being the input, do that. And a program will look something like this. You'll have, in the case of state 0 and 0, do this. In the case of state 0 and reading a 1, do this. In the case of state 0 and reading a blank tile, do this. In the case of state 1 and reading a 0, do this. In the case of state 1 and reading a 1, do this. In the case of state 1 and a blank tile, do this. So that's all a Turing machine is. And Alan Turing suggested that any problem that could be solved can be solved using this system. While it's never been mathematically proved to be correct, no one's ever disproved it either, but a lot of people have tried. So it's accepted now that, yes, anything that can be solved using this. So in other words, anything that a computer can do can be done using something as simple as this. This is a simplified, fully abstracted computer. So to try this out, let's get rid of this for a second. To try this out, there are a couple of links to Turing Machine simulators. I've linked to two of them because one of them is really nice to use but doesn't cover the universal simulator really well. The other one is a bit more pernickety to use but does cover a universal machine, which we'll get to later. So I'll start with the easy to use one first of all. Now, this just runs in a website, so we shouldn't have any problem running this at home. Right, so this gives you an example of how you can do it. It tells you what the syntax is. So you can give the name the initial state. So let's do, running out of screen real estate on this. Let's do the one that was in that presentation we just looked at. So I'll bring this over here. There we are. I'll scroll that down to there. Okay, so I'm going to try and run a simulation for this particular Turing machine using this transition function. So on this one here, you have to give it a name if you want. Well, I'll just call it Bob. The initial state, I'm going to say will start in state 0. So I'm just calling S0, S1, etc. Now this one has an accept state to say that, like a finite state automaton, once the Turing machine is finished, we either accept it or reject it. That's not particularly necessary. Doesn't matter. Most of the Turing machines don't necessarily need this, but it's there as an option if we want it. So I'll just call it S1. Doesn't matter. And then we put in all our delta functions. So it's delta, not sigmas. We put in all our delta functions, and left and right and stay where you are those things. Underscore means a blank cell. So you put the current state first, then underneath the new one. So I'll put in here, the first one is going to be if I'm in S0, comma, and I'm reading a 0, then underneath we put the output. So the output will be S0, it'll leave it as a 0, and it will move that way. So that's following this syntax for that first delta function of this transition function. Okay, the next one is if I'm in S0, so I'm looking at this one here now. If I'm in S0 and I'm putting in a 1, I go to state 0, I leave it as a 1, and I move that way. Okay, and you can put in all of these into there. Once that's done, this down so we can see it a bit better. There we are. So once that's done, we can compile it. It's like I made a mistake. 918 symbols must be single characters. So I missed a comma or something. 18. Oh, this is all the example stuff. So let's take out the rest of the comments. There we are. Compile it. Yeah, seems happy now. So then we can put in a tape. So I'll put 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Load that in. There it is, and it's starting there. And then we can step through it. Now on this one, I realise I put that in wrong. It should be that arrow going that way. So mine is stuck going left and right. I'll put that in there. Compile it. Yeah, load that, run it. So this one is, at the moment, every time it moves, it checks if it's a 0, it stays in state 0, so it's always in state 0, and it keeps moving to the right. Now this one's going to crash because I haven't told it what to do if I'm in state 0 and I reach a blank cell. So we get to there, and at this point it rejects because it's got to something that isn't defined. The next one on there tells you what to do in that state. So if I'm in state 0 and I encounter that, I should switch to state 1 and move to left. So let's put that delta function in. So if we're in state 0 and we encounter a blank tile, then we switch to state 1, we leave it as a blank tile, and we move that way. So I'll compile that, load that, and run it. So it now cycles through there, staying in state 0, always checking those top two ones, because it's encountering 1s and 0s, which it leaves them as they are and moves to the right. Once it's got to the end, it switches to state 1 and moves that way. At this point, it ends. It ends accepted because it ends in state 1, but it ends because it's reached something that's undefined. I'm in state 1 and I've encountered a 1. I haven't defined that, so therefore the program ends. Realistically, really, if I put these last three in, it should now define what to do for all the state 1s. So, could you guys finish this off, put in the last three delta functions in there, run it, and see if you can tell me what this Turing machine here actually does. It's a real program. It serves a purpose. I would say function or purpose there. I nearly came up with purpose. But serves a purpose. But could you finish off putting that transition function into that simulator, run it, see and tell what it does. If you can't get to work, post, I'll help you with it. I'll give you a couple of minutes to do it, then I'll come back. Okay, has anyone managed to get it working? Yeah, it's an inverter. So let's finish it off. So put the rest of them. So if we're in state 1 and we encounter a 0, we go to stay in state 1, we output a 1 and we move that way. If we're in state 1 and we encounter a 1, we stay in state 1, we output a 0 and we move that way. If we're in state 1 and we encounter a blank 1, we go to S2, which is our finished state. We leave it as that and we go that way. So compile that, load that and run it. So when we're in state 0, we're moving to the end of the string without changing anything. Once we encounter the end of the string, we go into state 1 and then we move all the way to the end, inverting them. So this is just a binary inverter. And once it reaches that, it goes to state 2 and that's the end of it. We're back where we started. The reason I made it go to the end first before going back is there's no guarantee that it's always going to start on the very first one. It could start on this one, so it works its way to the end before going back and changing them. Okay, did anyone else get there? I'm not getting any comments coming through at the moment. I'm hoping people are still on board with this. People haven't just loaded up YouTube and then gone and had dinner. Okay, so that's what a Turing machine is. Now there's some importance to this. Now, obviously this isn't a real thing. We can simulate it by effectively simulating infinite tape. We can't simulate infinite tape because eventually we'd run out of RAM and wouldn't be able to do it. But we can simulate it by having effectively infinite tape, and we simulate it on a computer. But what's the point? We have computers that are far easier to program than this. Why is it a really important thing? Well, essentially it proved something using the universal Turing machine. So Turing took this idea and then proved something could be done with it. If we load up the other one, so let's just move this one out of the way. Try and click on that, that's not the right one. So this out of the way, and we go to the other simulator, which is nowhere near as nice, but has a universal Turing machine in it. So this is another Turing machine simulator, and I'm going to load example program, universal Turing machine. Right, so what Turing then proved could be done using this Turing machine is you could program a Turing machine using a Turing machine. So instead of the transition function being programmed into the machine, instead of it being hard-coded into the machine, which is what everything is so far, the transition function could be on the tape. So this is the tape here. The first part of that tape is the transition function it wants to be used, and the second part is the value it wants to be used on. The actual transition function used to make this universal Turing machine is this. It's difficult, but it shows it's possible. So essentially what this does is emulate a Turing machine by taking that as taking that transition function and applying it to that value. And that worked. But it's very hard to see what's going on when we run it. So it goes to there, so it's reading, it keeps encountering a value, going back through here to see which delta function applies, does various stuff with it. So this one what we could have done is stuck all of that part into here and just made a standard Turing machine. But the universal Turing machine was proof that you could make a programmable computer. Don't forget, all of this was done before any programmable computer was ever devised. What he did with this was prove that it is possible to create a machine that can solve any solvable problem. Not only that, that machine can be reprogrammed to solve any solvable problem. Rather than create, well, here's a device that solves this problem, here's a device that solves this problem. Here is a single device, and we can tell that device how to solve any solvable problem. And this was in the 30s. He proved through this that that could be done. Now, of course, we know that can be done. That's what a computer is. It's a device that can be programmed to solve any solvable problem. But the universal Turing machine as a concept was proof that that could be done before it was ever even devised. That's why Turing's referred to as the father of computing for this kind of stuff. He showed proof that a programmable computer could exist way before it did. So we'll have a look at the kind of questions that can come up about a Turing machine. Ultimately, you need to be able to understand what it is, be able to describe what a universal Turing machine is and why it's important, and then you'll be able to step through transition functions if necessary. So let me just get the questions up that we could get. There we go. I'll come back to that in a second, actually. That's part of something else. In fact, there's a really good Tom Scott video on that. I'll link you to it. But we'll do these first, actually. So, I wanted to put this in here. Okay, right, I'll cover this now as well. It's interesting. The halting problem. This is a very specific problem. Again, Tom Scott, if anyone knows YouTuber Tom Scott, he's very good at explaining complex things in really simple ways. He's fantastic at that. He, in the last few weeks, did a video about this, and I'll link you to it. The halting problem is saying, well, let's say we're writing a program, okay? And this program has it's quite a complex one, and what we don't want is to run the program and find we're stuck in an infinite loop. You've all done it, you've all written a program, you've all had a while loop that has an incorrect criteria and it sticks there forever, it hangs, and we have to force quit the program. Now that can be quite catastrophic if you're running on dedicated hardware, or you're running on a microchip or something like that. So what was proposed is, well, could you write a program that can scan through another program and determine whether or not it will get stuck in an infinite loop? So could you write a function that can scan a program and say, actually, this will exit, this will halt, or it will run forever? And there is a fairly straightforward mathematical proof to say that problem cannot be solved. It is not possible to create a program that can determine whether another program will halt or whether it will loop forever. It simply can't be done. It's an unsolvable problem. The significance of this is that proves that there are some problems that cannot be solved. Not just are intractable, not difficult to solve, but just cannot be solved. It mathematically cannot be done. And the halting problem is an example of that. So the question here is actually asking a couple of different things. It requires you to know two things. Why is it not possible to create a Turing machine that solves the halting problem? Well, it requires you to know two things. First of all, that a Turing machine can solve any solvable problem, and that the halting problem is an unsolvable problem. So it's not possible because the halting machine is an unsolvable problem, and Turing machines can't solve unsolvable problems. That's for that one. Just while we're on this, another question that does sometimes come up is, say, what's the difference between an unsolvable problem and an intractable problem? In fact, I've just about finished marking the things from last time. It's so much harder to mark when you submit them online. I'll get those back to you next lesson. On the last assessment point we did, there was a question about intractable problems. and most people wrote the answer to an unsolvable problem, not an intractable problem. So an unsolvable problem is something like the halting problem that mathematically cannot be solved. What's an intractable problem? Yeah, essentially yes. It's one that can be solved. A solution exists for it, but it's one that is not going to run in a reasonable time frame on current hardware. It's generally accepted as tractable as anything that is exponential or above, the big O notation. It's intractable. So it is perfectly solvable. So the travelling salesman is perfectly solvable. It's just try every single route and take the one that had the shortest path. That's a solution. It's solved. But it would take millions of years for computers to do that for anything above about 10 cities. So that's intractable. Unsolvable is this. Mathematically cannot be solved. So I just want to cover that one there as well. Right, so look at the next question. To define a Turing machine, a finite alphabet of symbols that it can use need to be specified, and there needs to be a tape. State 2 other components of a Turing machine. So I'm hoping someone other than Aidan and Tom are still here, but I haven't heard from anyone else in quite a while. The reader thing, yep, the read head. What else it can need? Yep, the transition function, the set of instructions, the read head. Anything else? Well, as it says in here, so a set of states are needed, the set of transition rules, yep, the read-write head, yep, a set of accepting and halting states, if we do it that way, and storing the current state. Those are things it says there. Okay. Explain what a universal Turing machine is. That's a pretty catch-all question, and have a stab at that one. Although I'm starting to think there's only 3 people left here anyway. I think everyone else, actually, we've gone down to 11, a few people have gone. Well, we'll do this, we'll wrap this up for now, and then I'll do some more on Turing machines next lesson. In fact, yeah, we'll leave it there. I'll leave you that one. Explain what a universal Turing machine is. When, at the start of Thursday's lesson, that's what I'm going to ask. I want you to be able to write succinctly, in a way that would get you 2 marks, what a universal Turing machine is. That's the question we'll start with. We'll then look through the kind of questions that come up after that, which are ones like, I think the next one is one of these. Not quite. Yeah, ones like this where you're given transition functions and you're asked to say what state will it be and all that kind of stuff. So some step through ones exist. These are really nice ones if you get questions like this, because they're usually quite a lot of marks with pretty straightforward work. But I'm starting off by asking, what is a universal Turing machine? Okay, so I'll leave that there for now. We've had the concept of a Turing machine. On Thursday's lesson, we'll look at the kind of questions do for it, and I'll actually set you some questions that I want you to send to me as well. So if anyone's got any questions about what stuff we've done today, ask now. I'll give it 5 seconds because of the lag. Okay, if not, I will see you all on Thursday for the online one, and I'll see a lot of you on Monday in real life, which will be great. Okay, see you Thursday.